quickly learned that everything having to do with generating data sets for an AtLab just blows out any assumptions about software or hardware quality that you might have. And so uncompressed, the ZMAP data is 9 gigabytes. It's compressed, it's reasonably more useful. Plus, since you have those nice boxes you saw, the white boxes around each overlay, which meant you had to not only generate the overlay images, but store the dimensions, the minimum, maximum X and Y dimensions, and store those in a usable format too. And when you have a whole team of annotators waiting for feedback on whether what they did actually worked and was correct and was acceptable, you have to do a fast turnaround. They do a set of annotations, and then they say, when can we have the overlays? And originally the answer was 2 weeks. And that was just, not acceptable, for a live team to get feedback. We wanted to reduce that to days, and that was the essential challenge. Especially when we went from the product started out as simply axial images. Then we went to the coronal and the sagittal images, which meant we had to, in order to do the overlay processing, we had to recast those TIFF images, which were in the axial orientation. We had to create another set, which were in the coronal orientation, and a third set, which were in the sagittal orientation. And so the initial challenge that we had was simply doing that in a reasonable time frame. We tried using standard image processing utilities to extract individual lines from the files and reassemble them in different orientations. That just took too long. It was just they didn't have the intelligence about the individually compressed TIFF sections. So what we had to do is, since we were on a tight schedule, is we basically adapted the ZMAP code that we had for reading individual pixels and rewrote it so it would extract lines, a single line at a time rather than a single pixel at a time. And that was the only thing that was fast and flexible enough. And we derived the ZMAP code from code that was on the Ticklers Wiki for processing TIFF image data. And it was clearly written, flexible, and reliable enough so that we could simply adapt the code that we had to a new use. And so that was very useful for us because we could do it quickly. And it turned out not only did it met the schedule, but it was the only thing that did it fast enough to be practical for us, doing the individual extractions. So that is that. But that was only one part of, once we had those reoriented TIFF images, then came the real work of generating the overlay files and running on multiple I had a single very powerful desktop computer. It was still taking weeks to do the generations. We decided to split the only practical way to scale up the task was to split it over multiple computers. What we found very useful was combining an approach where we use both TCL and Make. And Make is for more than just building stuff. It's a very nice and straightforward way of parallelizing a task. So you define Make rules that can be done separately and individually. And Make has nice abilities to control things in terms of you can specify the number of parallel jobs that can be done at a time, as well as a load average, so you don't accidentally bury your computer and work. And so we redefined the task of generating the overlays into a combination of TCL and Make, where we would actually use TCL to generate Make files, specify Make files for a specific part of the task, and then the Make files would actually call TCL programs to script information to actually carry out each individual task. And that brought things down to about a week, which was on the outer edge of acceptability in terms of turnaround time we wanted for overlays. So the final frontier that we tried was to actually make use of what Amazon was bringing online as we were working, which was the Elastic Compute Cloud service, where you can spin up virtual servers on demand. And we used the most powerful computer virtual servers they had, which were 8 cores, and large amounts of RAM. The idea was that in order to improve the scalability of the product, we would upload all the overlays to the Amazon Simple Storage service so that at any one or more actual individual servers running the InatLab program could all access this one scalable Amazon store. So the task was to generate the overlays, upload the overlays to the Amazon S3 service. There's a lot of promises about the performance of cloud computing. In reality, there's a lot of glitches. So the solution was to make the process as robust as possible, and that was done by combining TCL Make, which has Make not only allows you to parallelize a project, it also helps you recover from errors. So if you detect an error, just kill the process, start it over, and you don't lose a lot of ground. Plus, we made use of Fossil to initialize our server images. That turned out to be a very useful tool, where we could quickly edit our scripts, upload them to Fossil, and then we had an automated virtual server script which would actually download all the scripting information needed for a particular run. So it was automated and simple and quite reliable as well. And that currently we can do a whole run of overlays in just about 2 days, which we find acceptable for the moment in terms of time for giving feedback to our annotators. Okay, now I'm going to hand it off to Steve Landers.
Okay, I'm going to skip some stuff because you really want to see the pictures. Suffice to say, we use Tcl HTTP as our web server, using some techniques that Colin showed me to actually do suspended calls, REST calls. Now, the real fun stuff is the 3D stuff. The quid pro quo for me having to do all the JavaScript is I get the toys at the end. What we're seeing here is some ImageMagick commands that I use to make a bunch of masks. Skip over this stuff, sorry. The fun stuff. Not only can we go from X to Y positioning to RGB to a particular structure, we can actually go from the RGB the other way. And so we start to render to do some fun stuff, rendering groups of structures individually and trying to get some 3D stuff out. Now, at the first attempt, Steve did this. We're thinking we might sponsor lunch next time. So basically, he's laid a series of images one on top of the other to get 3D. But it's still, you're seeing the entire section. So with this image technique, I came up with a technique that basically goes from, I'm provided a spreadsheet containing structure name list of RGB values by our anatomist, and I fire that into some make files, which do parallel makes across a number of processes, which basically mask out the information that we're not interested in, leaving the information we're interested in. So we end up with a section, a new axial section, which just contains particular structures in the system. And then I trim that down and resize it and so forth. So for example, here, sphenoid sinus, you can see the actual ImageMagick commands in the paper. But basically, I'm going from this ZMAP image, picking out the sphenoid sinuses, which are these ones here, and ending up with a little mask, and then when that mask is applied over the original section, we just get the sphenoid sinuses. I think that's what they're called. And so we fire that through the make file, and we end up with, on the right-hand side, you see the masked out image. So we do that for every section that a particular structure or group of structures on. Back through this thing again. Now, this is an interesting one. I had access to an 8-core Mac Pro last week. I was able to do make-J16 and continue editing. I sent Steve the make file and he said, "Lie down, man." I think he was concerned. He told me to limit it to a load average of 6. When he told me that, it was running at 36. So you can do a lot in parallel. And what we end up with, this is an example where I've actually stripped out the the skin and the subcutaneous fat and stacked them one on top of each other, and we're now looking down at the guy. I nicknamed him Mr. Chunky, a name which is stuck, unfortunately. There's another view of him. That's, again, just upper torso, skin, subcutaneous fat's gone. This is an old one, Cindy. You can see the artifacts from where it, yeah. Okay, but what you really want to see is some 3D stuff. So, all right, this is the gastrointestinal tract from the mouth to the anus. It's not too bright. This is when I was learning to do this stuff. You can also very faintly see some of the vascular system down there. How many of you eat offal? Let's show you another one. Full screen. This one is just the vascular system for the gastrointestinal tract. It's a bit hard to see. We'll put. Oh, thanks. We'll put these up on your some of these will go onto your memory USB stick. So what we're seeing here, this is A for anterior. As I turn it around, we've got the left side, and we've got the posterior view coming up, and now the right side. So that's the spleen. That's the aorta. Is that right, Mike? Yeah. That would be the vena cava. This is the vascular system for the liver, and then the arteries going down to the rear end. So we can do all of this sort of stuff. I don't know what that is. Do you?
Splenic artery.
Splenic artery. So what we've done here is taken a series of sections that just contain the structures we're interested in, thrown them into a program called OSIRIX, which is an Apple-based tool, which is just a graphical front end to VTK, a visualization toolkit, which is itself TK-based, TK-based. And then I've done a volume rendering, essentially a ray tracing through that to get a three-dimensional model, and then generated a QuickTime virtual reality off the back. On the 8-core machine, I can, within maybe 5 minutes of starting the process, I can be looking at this on the screen. 40 minutes later, I have the QuickTime virtual reality movie, which comprises 1,600 images. We might play Spot Your Organ later if you're interested. Okay, this one. This was done last Wednesday or Thursday. We're just getting better at it and having some fun. So this one is the pelvis and the femur. So you can see, now these colours are actually the colours of straight from the cadaver. This has already been used by Maury Pescatelli, the anatomist, anatomy professor at UIC. And Maury's pretty excited about all of this, because not so much this one, but he asked me to render this one here with some of the additional muscles attached. And now the students can start poking around and seeing how it all comes together. If I knew much about anatomy, I could tell you which...
But that's one of the more difficult areas of teaching gross anatomy. It was a huge help to Maury in the lecture just to be able to show them this in 3 dimensions without all of the other stuff in the way.
Now, clean some of these out. This one's interesting. This is my favourite one. How about this? Doesn't that make you... It's amazing how it all hangs together, isn't it?
So they said monsters.
Yeah, okay. It's funny, when I started on the project, I used to take my steak a lot rarer than I do now. Okay, so now Maury was teaching the diaphragm last week to the med students and the physical therapy students. So we said, right, let's render that structure with the diaphragm. We'll render the diaphragm first. I won't put that in full screen, but you get the idea. That's the diaphragm. It was actually quite useful, because Maury immediately came back and said we need to improve the annotations on that. It has fenestrations, whatever they are, windows, I'm told. But for the students just to be able to do that and get a feel for it, but then he said let's render it in place. And now you can just see the diaphragm under there, tucked up under there. The nice thing is the students can do this. And you start... Well, if it was an anatomy lecture, Mike would explain the 3 portals through the diaphragm and their function and all the rest of it. Also, when we first rendered it, this clavicle was missing. Maury forgot to put an X next to the clavicle in the spreadsheet. So we put it back in and called it the well-tempered clavicle. Okay, and the final one was, I was a bit concerned that the diaphragm was so pale there, so the last rendering I have to show you, what I've actually done is drop the opacity of the skeletal structure, but left the opacity of the diaphragm itself, and so you can get a better feel. And this was done in a rush, so it's compressed in the in the Z direction, but you get an idea of where the diaphragm sits in relation to things. And that's pretty much all I've got to show.
So, other questions?
How do we do that?
Well, it's an online service. We can give you a login.
Okay.
Yeah. Just send me an email. We can get you a login.
We do track everything that people look at, so if you start looking at the naughty bits.
I've got an 18-year-old daughter who's just starting college,
Uh-huh.
who thinks she might be interested in medicine, and this would just blow her mind, because she's all into technology.
My oldest daughter took gross anatomy as a senior in high school, and so about a year ago, in fact, you guys saw this a year ago, in a much more primitive version, but I gave their teacher a login, and she used it several times to help teach part of that course. So, you know, we decided if we design this to satisfy the needs for medical students, that it's sort of a pyramid in terms of the user base, because if it fits their needs, then of course it's fine for physical therapy and nursing, and then you go down a little farther and suddenly get a large number of users in like physician assistance programs, and go to lower and you get huge numbers of students in college level biology and even high school levels. So it's worked out pretty well.
Did he have any pathology that you can call attention to?
Well,
I'm interested in what
yeah, actually, they're,
You want me to?
go ahead.
Okay. There's a door prize. There's a door prize if you can find the missing piece. And those of you who know, and I know there's a few of you, don't mention it. We might go up there here, I think.
Seeing parts we don't want to see.
All right, Mike will just share the information. Too high, was it?
Yeah.
He's missing one.
He's missing one, right?
missing one?
Yes, missing one.
Roy.
So, I'm wondering about things you found good, bad, or missing in using Tickle on this problem.
Well, we couldn't use Tickle on the client side, and we would love to have done more with Tickle. JavaScript's a fine language, much better than some of the other alternatives, but I would have loved to use Tickle in the browser. And maybe we will in the future. We're investigating how we can do that.
How would that have changed how you had to write the code if you were ever used Tickle?
There wouldn't be a forehead-sized indentation in my desk. Yeah. The problem is my problem, these guys didn't have it, I was flipping between Java and Tickle all the time. And when you start to put / comment in your Tickle scripts,
JavaScript.
a JavaScript and Tickle, I should say, yeah.
We actually did have Java in the very early version of this, because that ZMAP decoder was originally coded in Java for reasons I won't go into. And we were so fed up with having to keep this Java piece in the system that Steve Huntley recoded it entirely in Tickle using that TIFF decoder code from the wiki, and it was, 5 times faster?
That's more stable,
Yeah, much more stable.
You could have just put like a / command and had it do nothing.
Yeah, I could. Hence just saying I need to create a / command. Cindy's got something, yeah.
Just, I forgot to say two numbers that the annotation team would kill me if I didn't say. So over the summer, they annotated 11,000 annotations, and they created about 100 new objects.
So it
Put
gives
the
you an
data
idea of the manual labor involved in creating this knowledge base of the program. No matter how much automation we build into the system, we still haven't been able to get rid of the expert and the need for the expert. We gotten good enough at it that, a couple, PhD level anatomists can manage a group of medical students, and it works quite well. But it's a tremendously labor-intensive process at the front end. But what we get out of the back end is an incredibly high-performance system. One thing we didn't talk about that you guys are probably going to mention some of this tomorrow at the start of this thing, right? The fact that we went to the cloud for improving the performance and scalability of the deployment system as well, and the runtime system. And this whole process took us from a system that worked pretty well, for just a couple of users at a time, where at least theoretically we ought to be able to handle thousands of users at a time.
I have a question. I have two questions. The first one is, which part of the code is parallel? Display or data accessing?
The parallelization comes into the data processing side of things, where we're going from those annotations through the steps that Steve Huntley was talking about, and steps that Steve Landers was talking about, generating the different kinds of data that those annotations sort of lead to.
Yeah, for the parallelization, I only know the MPI or OpenMP. I haven't heard about MAVE, so is it the language? I don't know.
Standard Unix facility. We do use OpenMPI, well, MPI-CH actually. We use it in other things. But it's a build system, a parallel build system. It's a standard part of Unix, and you declare these files and describe what you want to do them for you, and you can do it parallel. So it's actually a different problem than OpenMPI and MPI-CH solve.
Over the years, we've looked at using parallel real-time visualization engines for different things as well, and we spent some time playing around with VTK and Paraview, thinking of using it for some things, and we'll probably come back to that in the future. So more of what you saw leading up to Steve being able to rotate the individual organs will be able to be done on demand in real time.
Okay, Ed, any other questions? Can we please take offline? We're a little over time here. Next, our next talk is by Dr. Richard Hipp, SQLite Tree, the most used TICO extension.
Yeah, the number of times I have to get Richard's video on the internet working. There we go.
Right, yeah, you got to put the cable plug this in. Okay, how much time do I have, Gio? Go ahead and take the whole half hour. Okay, well, only a half hour. I have 95 slides. So this is the URL where you can download the copy of the slides as of early this morning. I've been making changes and haven't been able to upload a new copy of the slides because of networking problems, but you might want to get a copy and do not blink. Title of my talk, what the world's most popular TICL extension is SQLite. For the longest time, I kind of hid the relationship between SQLite and TICL, but I'm coming out with SQLite. SQLite is a TICL extension, bottom line. SQLite, as far as I'm aware, is the only SQL database engine in the world that was specifically designed to work with TICL. I mean, there are lots of SQL databases out there. You're familiar with them all. You can probably access them all now that you have TDBC. But you know what? None of these other guys are designed to work with TICL. They might work with TICL, but they're not designed to work with TICL. Only SQLite is specifically a TICL extension. Now, why do I say it's a TICL extension? Let's go back to how SQLite got its origin. I was working in the 90s on a a thing, and this is just like one diagram out of 750. It's a big industrial plant, and they had tens of thousands of valves and pumps and pipes and meters and gauges and stuff. And I had to do some really complex computations on this. It involved the subgraph homomorphism, which is an NP-complete problem. It was really complicated. Very interesting story. But to make a long story short, all of the data for this thing is coming out of an Informix database, which is a typical client-server database engine. And that worked great as long as Informix was running. But what would happen is the people who operate this program would, for whatever reason, decide to periodically power cycle the server. And when they would do that, sometimes the server, or the Oracle server would not Oracle, it's Informix server, would not come back up. And when Informix didn't come back up, then obviously the client processes could not talk to the database. And when that happened, the client processes had to put up an error message. Did I mention that all this was done in TickleTK? Well, there's some C code as well. I used a lot of C code to do a lot of the heavy numerical lifting, but the interface is all TickleTK, and a lot of the glue code to kind of pull all the modules together was in TickleTK. So anyway, I pop up this dialog box, and everybody get real mad, and they get mad at me because it was my program that brought the dialog box up, even though there was nothing I could do to prevent this from happening. So I had the idea, well, why do we need this Informix server anyway? Why can't we just have the program talk directly to the database files on disk? Why does this server have to be there? And that way I reasoned that if the computer was healthy enough that they could double click on the icon to bring up my program, then it should be able to get to its data and do its thing. And that's how SQLite got started. It really started as sort of a layer that sits between the TickleTK application and the disk drive and translates high-level SQL statements into lots of little low-level reads and writes. Sort of a translator layer. Don't think of it so much as a database, but as a translator. So, well, maybe you're thinking now, well, why do I care about SQL in the first place? I mean, what's the big deal? SQL is really important because it allows you to program at a much higher level than you would be when you're doing this kind of data access steps. If you're familiar with like formal methods, you might recognize that SQL statements are very close to being high-level requirements. And so if you're working in a requirements-based environment where somebody hands some requirements, you have to code to it. Very often, there's like a one-to-one mapping between a statement in SQL and a high-level requirement. And so you don't have to go through the entire derived requirements, low-level requirements, and all of that. You just type it in and it goes. Your program by specification. With SQL, you're telling the machine what result you want. You're not telling it how to get the result, which is very different from most other programming. This allows you to specify what you want very quickly. And so you spend more time thinking about your problem, how your user is perceiving your application, and you get to focus on your product. It allows you, the programmer, to maintain situational awareness. Now, a lot of people say, well, situational awareness, that's just a buzzword. But I contend that it's very important to maintain good situational awareness, because if you lose that, it can have very serious consequences. People might also say, well, you know, I'm just doing name value pairs. And if you're doing just name value pairs for your data, an array works fine. You don't really need a database engine to do that. Where SQL comes into play is when you get more complex queries. Here's an example of a real-world query that comes out of a real-world application. And how many lines of Tcl code do you think it would take to encode that? 100, 1,000? You probably know. You know the application. How many people here use Firefox? You know, on Firefox 3, if you start typing into the URL bar, it gives you lots of things that you have recently visited. You know, every time you press a key on the awesome bar, they call it, it runs some SQL that looks approximately like that. I say approximately like that because the Firefox people are changing this about once a week to try and make it go a few milliseconds faster or something. But you know, how many thousands of lines of, I guess in the case of Firefox it would be JavaScript code, how many thousand lines of JavaScript code would you have to write in order to replace this one query statement? So SQL can be a very powerful thing. Other benefits of SQL and SQLite is that you get persistent storage, you get transactional capabilities, which are very powerful. You get your database is cross-platform so that you can move it from machine to machine. SQL, according to O'Reilly, which we heard about this morning, according to Tim O'Reilly, SQL is the most widely known programming language in the world. More programmers know SQL than any other programming language. So it's widely known. It turns out that when you use SQL, you focus so much on the higher level aspects that you end up writing faster programs. And it's also more reliable. You're much less likely to make a bug or a mistake writing a few lines of SQL than you are thousands of lines of code. And finally, and I think this is a very important point, what I've found over the years is that SQL is very good at a few things that also correspond to the very few things that Tcl doesn't do so well. I mean, Tcl does most things really, really well. There's a few things it's a little weak on, and SQL is very strong on those. And so SQLite and Tcl-TK sort of form a really nice synergy. And it makes application programming a whole lot easier that way. So earlier today, we were talking about small languages, and I just happened to throw this in here. So SQLite is a small language within a small language. Is it like a meta small language? I'm not really sure how that works, but anyway. So let's dive right in and find out how you use SQLite in your Tcl programs. The first thing you need to do is load it because it's not built in. I'll have more to say about that in a minute. And then you declare an object. You say SQLite3. When you load the SQLite package, the only name that's added is the single command SQLite3. So it's not in a namespace. What's the point of having a namespace if you only have one command, right? So you do the one command and you create this object called DB, and you tell it the name of the database file that you want to open. And if the database file doesn't already exist, it'll create it for you. And that creates this DB object, which you're going to use from now on. And so then you say DB and then a method eval, and then you give it lots of SQL that you want to execute. And in this case, I'm doing a create table statement, which is going to create a table for me. And if you're not familiar with SQL, just really quickly, a create table statement is going to create a unit of storage called a table. It's going to have 3 columns in this case, which, of course, you can have as many columns as you want. There's no real limits. An interesting thing is SQL has these data types on there. And every SQL database engine in the world that I'm aware of is pretty strict about enforcing those data types because that's just what SQL does. But SQLite, because it began its life as a Tcl extension, doesn't really work that way. It kind of ignores the data types. As I say, traditional SQL database engines are very rigidly typed. And if you say this is a bar